evaluate the limit. We have the limit as x is approaching 1 from the right-hand side of x raised to the 1 divided by 1 minus x. So we'll start this problem off by attempting to evaluate. So we're replacing every x with x approaching from the right. We have 1 approaching from the right raised to the 1 minus 1 approaching from the right-hand side. And so we know with this rational expression here that we have 1 over 1 minus x. So we can say that here is a vertical asymptote at the point x is 1. Here's our x-axis and our y-axis. And we know that the graph looks like such. And so we can see here that as x is approaching 1 from the right-hand side, that the y values are approaching minus infinity. So we can say that we have 1 approaching from the right raised to a negative infinity, or even simply 1 raised to the negative infinity, which is undefined. Since we have shown that our limit, when directly evaluated, is in an indeterminate form, we can now apply L'Hopital's rule. So we have the limit as x is approaching 1 from the right-hand side of x raised to the 1 by 1 minus x, and we're stuck. We want to recall that L'Hopital's requires the argument of our limit to be a quotient. So we have the limit as x is approaching x naught of a function f of x divided by g of x. So we need to go ahead and rewrite the argument in the form of a quotient. So in this case, in order to rewrite our argument, or the inside, as a quotient, we're going to have to slightly manipulate our function. So we want to rewrite it as a quotient f over g. So in order to do this, we actually want to consider the function that this limit is coming from. So I'm going to let y be equal to x raised to the 1 divided by 1 minus x. And now in order to create a quotient, we can apply the natural logarithm to both sides. So we'll have the natural log of y is equal to the natural logarithm of x raised to the 1 by 1 minus x. So our left-hand side stays as it is. This is the natural logarithm of y. But by the properties of logarithms, this power will now come to the front. Again, that's by the algebraic properties of logarithms. Remember, if you have the natural log of some a raised to the b power, that b can come out to the front. So applying that here, we have the natural log of y is equal to 1 divided by 1 minus x multiplied by the natural log of x. And so now we see that we have a quotient, the natural logarithm of x all over 1 minus x. So we'll just need to be careful here. Right? The quotient that we're using is not the original expression. Right? Notice we have on the left-hand side the natural log of y. So we'll need to make sure to remove that so we can get back to where we started. So we're ready now to evaluate the limit. So we can even think about this as, so we started with the limit as x is approaching 1 from the right of y is equal to the limit as x approaches 1 from the right of x raised to the 1 minus x. And in order to apply L'Hopital's, we rewrote this in an equivalent form. The limit as x is approaching 1 from the right, and this is now the natural log of y, which is equal to the limit as x is approaching 1 from the right of the natural log of x all over 1 minus x. And in this form, it's now safe to apply L'Hopital's rule. So we can now apply a L'Hopital. So taking the derivative of the numerator and denominator separately, this becomes the limit as x is approaching 1 from the right-hand side of the derivative of the numerator is 1 divided by x. The derivative of the denominator is negative 1. So we have the limit as x is approaching 1 from the right-hand side of negative 1 over x, which we can evaluate. That's minus 1 all over 1 from the right, which is just going to 1 in this case, and we're left with negative 1. So what this is showing us, again, we want to be mindful, what we have here is that the limit as x is approaching 1 from the right-hand side of the natural log of y is equal to negative 1. But we want to remove this natural log. Right? That natural log of y isn't in the original expression. We want to just have y. So to remove this natural logarithm, we can apply the exponential, and this is not a very nice way to put this. We'll write this a little better. So to remove that natural log, we apply the natural exponential. So we apply the natural exponential to both sides to simplify our limit. So I have the natural exponential raised to the limit as x approaches 1 from the right of the natural log of y is equal to the natural exponential raised to the minus 1. And here on the left-hand side, we can even pull that limit to the outside or pull this exponential in. So this is equivalent to the limit as x is approaching 1 from the right of the natural exponential raised to the natural log of y equals e to the minus 1. And so now we see natural exponential, natural logarithm cancel each other out or undo the effects of each other. And we're back where we started. We have the limit as x is approaching 1 from the right-hand side of y is e to the negative x. And this is our beautiful final answer. And that's because y is what we started with. We had defined y as x raised to the 1 minus x.